Ever imagined a magnet so strong you could wipe your credit card from like 2,000 kilometers away?
Seriously, 2,000.
Yeah, I think the entire length of Italy. That, my friends, is the power of a magnetar.
Magnetars, they're absolutely mind-boggling. We're talking magnetic fields quadrillions of times stronger than Earth's. It's insane.
So today we're diving deep into these magnetic monsters. How do they even form? What makes their magnetic field so ridiculously intense? And what happens when these things, well, when they let loose?
Good questions. It's going to be a wild ride for sure.
So first things first, what is a magnetar? I mean, the name kind of gives it away, but...
Right. At its core, a magnetar is a type of neutron star.
Which is?
The super dense leftover bits of a massive star that's gone supernova.
Okay, so like a stellar corpse, but extra magnetic.
Exactly. It's city-size, maybe 20 kilometers across, but packs the mass of 2 suns, and that magnetic field defies imagination.
Wow. Okay, so how does a star go from shining bright to becoming, a magnetar? What's the process?
Well, it starts with a massive star, way bigger than our sun, much bigger.
Uh-huh.
This star eventually runs out of fuel.
Runs out of gas.
Right. And when that happens, the core collapses under its own immense gravity.
Crushing it down.
Exactly. Into a neutron star. But sometimes things get interesting if the star was already spinning really fast.
Okay.
And had a strong magnetic field.
Got it. Fast spinner, strong magnet.
Then during the collapse, the magnetic field gets, well, imagine squeezing a magnetic field. It gets concentrated, amplified.
Like a cosmic dynamo.
Exactly. The dynamo effect.
Oh, wait.
Amplified to insane levels. Millions of times stronger than a typical neutron star.
And boom. Magnetar.
Magnetar.
Okay, so we've got this super dense, crazy spinning thing with an unimaginable magnetic field. What can it do?
Oh, all sorts of crazy things. First off, the magnetic field is so strong it distorts atoms, like stretches them out into needle shapes.
No way. Atoms. Changing shape.
Yeah. It's wild. Then there are starquakes. The magnetic pressure, it's immense. And it can cause the magnetar's crust to shift. Suddenly.
So like earthquakes, but on a star.
Exactly. Starquakes. And these release enormous bursts of energy, gamma ray flashes.
Gamma rays, those are intense.
Very. And then the giant flares.
I've heard about these.
Magnetars can unleash these flares that, for a brief moment, outshine the entire Milky Way galaxy. The entire thing.
Seriously.
Seriously. We're talking energy equivalent to what our sun produces in 100,000 years, released in a fraction of a second.
That's a lot.
Welcome back, space explorers. Ready for more Magnetar mayhem.
Oh, I'm strapped in and ready for launch. Part 1 was mind-blowing, but I'm ready for some specifics. Like, what are some of the Magnetars out there that are really making waves?
Yeah.
The ones with, names and stories.
You want to meet the cosmic celebrities?
Exactly. The ones causing all the drama.
Well, let's start with the record holder for Magnetar outbursts, SGR 1806-20.
That name rings a bell. Didn't it cause a bit of a ruckus back in 2004?
You bet it did. Imagine, you're just going about your day here on Earth, and suddenly, bam, a wave of energy from a star 50,000 light years away slams into our atmosphere.
No way, seriously. That's crazy.
It was so powerful it actually messed with our upper atmosphere, disrupted stuff, and that was from 50,000 light years away.
Okay, so this SGR 1806-20 is basically a magnetar superstar.
A total diva, you could say. It holds the record for the brightest flare ever seen. And just to be clear, we're talking about a single burst of energy that was, for a split second, brighter than all the stars in our galaxy combined. All of them.
It's hard to comprehend that kind of power. Is it still active? Or was that 2004 flare like a one-time thing?
Oh, it's still active, all right. Thankfully, no galaxy-blinding flares recently, but it's constantly spitting out bursts of X-rays and gamma rays. Astronomers are definitely keeping a close watch.
So like a cosmic beacon constantly sending out signals for us to decipher.
Exactly. And every magnetar, they have their own unique signature, their own story to tell. Like take 1E1048.15937. This one's a bit of a mystery, really.
Okay, I might need help pronouncing that one, but what makes it so special?
Well, SGR 1806-20, that's our drama queen, all about those big explosive outbursts. But 1E1048.15937, this one's more of a slow burn. Think X-ray flares that can go on for weeks, even months.
Really? That's different.
Right. It's like it's holding a grudge against the universe, just simmering with anger.
So is it like a firecracker versus a slow, smoldering fire?
Yeah, that's a good way to put it. And honestly, we're not totally sure why it's so different. Astronomers are still trying to wrap their heads around the magnetic field dynamics at play here. Maybe it's the structure of the crust or the way the magnetic field is anchored within the star.
It's like each magnetar gives us a different piece of the puzzle. Like they have their own personalities.
Oh, I like that.
Okay.
Personalities. And speaking of personality, our next magnetar, well, this one's a bit of a chatterbox, XTE J810N197, one of the first magnetars we discovered that actually emits radio waves.
Wait, hold on. Radio waves. I thought magnetars were all about those intense X-rays and gamma rays.
They are, mostly. But some, like this one, they like to chat on different wavelengths. And those radio waves, they give us a whole new perspective. Tell us about the magnetic field structure, the environment around the magnetar.
So, like having another channel to listen in on, to eavesdrop on their conversations.
You got it. And when we combine all those observations, the radio waves, the X-rays, the gamma rays, we start to build a more complete picture of these incredible objects.
We got SGR Atino 620, the drama queen, 1E 1048.15937, the smoldering grudge holder, and XTE J810-197, the chatterbox. It's like a cosmic reality show.
I like that. But with all their differences, there's got to be something that unites them, right? Something that makes a neutron star a magnetar in the first place.
Yeah, that's the million-dollar question, isn't it?
It is. We know it has to do with the original star's magnetic field and how fast it was spinning, but the exact recipe, still a mystery.
So, like missing ingredients in the cosmic cookbook?
Kinda, yeah. Some scientists think those extreme magnetic fields are created during the star's collapse. The dynamo model, we call it.
Okay, that sounds familiar.
But others, they think maybe those strong fields were already there, inside the star, from the very beginning, like some hidden treasure. The fossil field model.
So are we talking like a cosmic puzzle with missing pieces?
Exactly. And the problem is, we can't just peek inside a collapsing star and see what's happening. We have to rely on computer models, indirect observations. It's like a cosmic detective story.
And probably a lot harder to recreate a collapsing star in a lab.
Yeah, just a tad. The densities and temperatures involved,
Yeah.
those are beyond anything we can create here on Earth. But that's what makes it so fascinating. There's always more to uncover. Like, one thing that really stumps us is how magnetars, magnetic fields, they fade over time. They decay.
So they're not forever magnets.
Nope. But we don't know exactly how they decay, what the mechanisms are. It's like a slow leak in a cosmic balloon. The energy is slowly dissipating, but where's it going? How fast is it happening? Big questions.
And those outbursts, could those be connected to the decay?
Maybe. Some astronomers think so. Like, maybe those bursts are how the magnetar releases some of that pent-up magnetic energy. A pressure valve, in a way.
So they're like, I'm too magnetic, gotta let off some steam. And then, boom, a giant flare.
Something like that. And then there's, well, this is where things get really interesting, the connection between magnetars and those mysterious fast radio bursts. Ever heard of those? FRBs.
Oh yeah, the super short, super intense radio signals from deep space. Those are still a bit of a head scratcher, right?
Big time. But in the last few years, astronomers have pinpointed several FRBs coming from our own galaxy. And guess what? They seem to be coming from magnetars.
Seriously. So these magnetic beasts could be responsible for some of the most powerful radio signals in the universe.
It's looking more and more likely. The current thinking is that these FRBs are caused by sudden shifts or reconfigurations in the magnetar's magnetic field, like a cosmic snap, releasing a torrent of energy that we detect as a radio burst.
So they're like sending out Morse code, but on a galactic scale.
Exactly. We're still trying to crack the code, but it's a pretty exciting clue in the FRB mystery.
Definitely adds another layer of intrigue to these already fascinating objects. But how do we even study them? What kind of tools can handle these cosmic heavyweights?
Well, luckily, we've got some pretty powerful tools in our cosmic toolbox. X-ray telescopes like Chandra, those let us observe the high-energy outbursts. Then there are gamma-ray telescopes like Fermi to catch those massive flares. And for listening in on their radio chatter, we've got radio telescopes, like the Very Large Array.
So it's like we're experiencing a magnetar with all our senses, gathering data from across the entire electromagnetic spectrum.
Exactly. And the more powerful our telescopes become, the more sensitive they get, the more we can learn. We're piecing together the magnetar puzzle, one observation at a time.
Sounds like there's still a lot more to learn about these magnetic monsters.
Oh, definitely. But before we get ahead of ourselves, let's take a pause here. We'll explore some of the bigger implications of magnetar research in Part 3. How studying these extreme objects can help us understand the universe. maybe even lead to new technologies. And yeah, we'll even touch on the potential risks they pose. So stick around, there's a whole lot more to uncover.
Back for more Magnetar madness. I gotta say, even after 2 parts, I'm still kind of reeling from all this Magnetar stuff.
Yeah, it's a lot to take in. It really makes you think, huh, about the universe, I mean, just how much we don't know.
Absolutely. So we've covered a lot of ground, what they are, how they form, those crazy outbursts. But now I'm curious, what's the big takeaway here? What can studying magnetars tell us about, well, everything?
That's the question, isn't it? I mean, on one hand, they're like these extreme physics labs, places where we can see physics happening that we could never recreate here on Earth.
Yeah, those magnetic fields are just insane. Pushing the limits of what we understand about, like, quantum mechanics, gravity, all that.
Exactly. By studying how matter and energy behave in those environments, we can test our theories, maybe even come up with new ones. It's like having a front row seat to the most extreme physics experiment in the universe.
It's mind-blowing that something so, I don't know, alien could help us understand the fundamental laws of physics. But are there any practical applications? Like, could magnetar research lead to new technologies?
Potentially, yeah. Remember how we talked about some magnetars emitting radio waves?
Right, those chatty ones?
Well, by studying those radio emissions, figuring out how they're generated, we might learn new ways to manipulate electromagnetic radiation.
So, are you saying magnetar research could lead to, like, faster communications,
Yeah.
better sensors, maybe even new forms of energy?
It's early days, for sure. We're a long way from directly applying those principles. But the potential is definitely there.
That's amazing. Okay, but let's talk about something a bit more, well, closer to home. We've mentioned that magnetars can be dangerous. Could one of those outbursts actually harm Earth?
It's a fair question. And the answer is yeah, if a magnetar had a major outburst close enough to Earth, it could cause some serious problems.
I mean, remember that 2004 event with SGR 180620,
Oh.
the one that disrupted Earth's atmosphere from 50,000 light years away?
Exactly. That was a wake-up call.
Not something I'd want to experience up close.
Thankfully, the odds of that happening are really, really low. All the magnetars we know about are far enough away that we're safe from any direct hits.
Okay, that's good to hear. But what about our technology? Could a nearby outburst mess with, like, satellites, communication systems?
It's possible. A powerful burst of X-rays or gamma rays could fry electronics, disrupt communications, maybe even damage power grids.
So like a cosmic EMP blast.
Yeah, kind of. But again, these events are incredibly rare. And the more we learn about magnetars, the better we'll be able to predict these outbursts and protect our technology.
That makes sense. So it sounds like magnetars. They're incredibly powerful, potentially dangerous, but also valuable tools for scientific discovery and maybe even for new technologies.
Exactly. They're a powerful reminder that there are forces out there in the universe that are way beyond anything we experience here on Earth.
It's both humbling and inspiring, you know?
Absolutely. It shows us just how much we still have to learn about the universe and how much more there is to discover.
Well, on that note, huge thanks for guiding us through this deep dive into the world of magnetars. It's been incredible.
My pleasure. And a big thank you to all our listeners for joining us on this journey. Keep looking up and keep exploring the cosmos.
And if you want to keep exploring the wonders of space and science, be sure to follow and subscribe to Cosmos in a Pod's Podcast YouTube channel for more fascinating deep dives.